All right, so in the previous lecture, we talked about the condition to have a matching in a bipartite graphs. Now we will work on more general graphs, and this is the part that was not covered in the discrete math course. All right, so our first goal is to understand the perfect matchings. In a general graph. So general means non-bipartite, because for bipartite graphs we knew everything. All right, and so we may ask, when do we have a perfect matching? When do we have a matching covering every vertex? Well, there could be some obvious necessary conditions. Right? So for instance, if I have a perfect matching, then number of vertices of the graph should be even. Right? Well, of course, right? If you have odd number of vertices, you can never make a perfect matching. That's true. Anything else? Well, actually, some of you may have thought about this. So each component has even number of vertices. Because if you do have a perfect matching, then every component has a perfect matching, and so every component must have an even number of vertices. Sure. But is that enough? Of course, that's not enough. What else can you say? Now, if I delete one vertex, then there will be a vertex which was paired with this guy by an edge in the matching. Then there are other vertices. Other vertices are like covered by matching. So then, what does component look like? Well, some of the components look like this. Some of the components may be over here. So what I mean is, if I delete this single vertex, then at most one component has odd number of vertices, and all other components must have even number of vertices. So for every vertex v, okay, well, actually exactly one component has odd number of vertices, right? Exactly one component of G delete V has an odd number of vertices. So let's say we say a component of G delete X is odd if it has odd number of vertices. Okay, now what happens if I delete a set of vertices? Let's say I delete 5 vertices, and potentially they may be joined to 5 vertices outside, and there are other vertices. Any component not touching any of these 5 vertices will have even number of vertices, and some components may touch it. Some component touches even number of them, but yeah, so this is odd component. This is even component. Yeah, so otherwise we say even. Okay, now what we can observe is the following. So G delete so the number of odd components of G delete X is at most size of X, because you had this X many vertices in that may screw the parity. All other components which do not contain any of these 5 vertices will have even number of vertices, right? So that's the condition. So that's the condition that we are interested. So let me say this notation. So the odd of G delete X is the number of odd components in G delete X. Okay, so far we talked about all these obvious necessary conditions in order for a graph to have perfect matching. Now, the surprising theorem of Todd says that this is actually sufficient. So this is theorem due to Todd in 1947. A graph has a perfect matching if and only if graph G has a perfect matching if and only if the number of odd components in G delete X is at most X for all subset of vertices. Okay, and we will see many theorems of Todd's in this course. Right? He's a Canadian mathematician who used to be a professor at University of Waterloo, and during the Second World War he served as a cryptographer in the army, in the British Army, decoding the secret keys of Germans. After the war, he came back to academia and worked on graph theory. He's one of the founders of modern graph theory. All right. So how do we prove this? So I'm going to show you a proof by using induction and Kinetics theorem, or Hall's theorem, the equivalent. So which direction is easy? Well, this forward direction is easy. We have already seen it. Whenever you have a graph, whenever you have a perfect matching, then for any set X, the number of other component is at most size of X. So that's easy, we skip it. What about the backward direction, the non-trivial direction? Right? So this is the proof. So we apply induction on number of vertices. Okay? And it's trivial if... Okay, now maybe we don't have to say that. So suppose that a number of odd components. So suppose we have the instance satisfying this. Now my goal is to reduce this instance to a smaller instance and apply induction hypothesis. So here's a sequence of claims. So the first claim is number of vertices is even. Why? Well, let's take X to be empty. The number of other component of G is at most 0. So that means G has no other components. So every component has even number of vertices. So graph has even number of vertices. Right? So that's okay. Now, let's say X is critical if it satisfies the equality. Remember we had a similar idea when we have a proof of Hall's theorem. Right? We try to find a set which satisfies the equality for this inequality. Now, well, there's at least one critical set. Why? Well, because empty is critical. Sure, that's not a problem. The third claim is if number bound component of G delete X is bigger than or equal to X minus 1, then X is critical. So why? Why is this the case? Let's look at the number of vertices. Oh, well, that's number of vertices in even components plus number of vertices even components of G delete X vertices in odd components of G delete X plus X, right? So you have a X, you have even components and odd components. And total number of vertices is this. And if we look at in modulo 2, then what remains is the number of odd components plus X, right? But we knew that number of vertices of graph is even by the first claim. So that means number of odd component of G delete X is always equal to X in modulo 2. So as long as we have this inequality, then they are equal because they cannot have different parity, so X is going to be critical. All right, so this is going to be the key property that we're going to use. So the proof of this Tut's theorem depends on the parity. Right, so what about the next claim? We will claim that, okay, so now we will choose a particular critical set. So let X be a maximal critical set. So from now on, my X is not an arbitrary critical set, it's gonna be a maximal critical set. Well, I'm now debating whether I should say, maximum or maximal, but let's see what happens. Okay, now here's another claim. G delete X has no even components. Why? Suppose it does. Suppose it does have even components. Now we want to find a bigger critical set. So let C be an even component of G delete X. Now I pick a vertex inside C. So this is my C. Now what we are going to do is look at the X union free. Alright, now let X prime be X union free. And what's going to happen? So the number of odd components in G delete X prime is what? Well, the previous odd components stay as odd components, so that's good. So that's the number of odd components in G delete X plus, and there's no edges from this C to other odd components, right? There's no edges like this, so this C will be split into smaller components, and at least one of them has to be even. So let me say inequality. At least one of them has to be even. Yes. And this is x plus 1. The same as says of x prime. Right? But actually it doesn't matter. Yeah, okay, let me simplify the proof. We can just say that. So this is equal to x prime minus 1. Right? And by the third claim, by the parity issues, this means the x prime is critical. And that's contradiction. This is contradiction because we assume that X is a maximal critical set. There's no other critical set containing X as a subset, as a proper subset. So that's the proof of the claim 4. Now, here's the sketch. Now, from now on, we don't have any even component, but we do have odd components. So what we're going to do is to pair them up. So our goal is to link vertices in X to some vertex in distinct odd components, and then what's left in the remaining, we will find the perfect matching, covering all vertices except this one vertex in each component. So that's the goal. So the next claim is the following. So for every odd component, C of G delete X and a vertex V of C, the C delete V has a perfect matching. So that's the claim that we have perfect matching here. And why? Here's the place that we're going to use the induction. Since C delete V, the number of vertices of C delete V is strictly smaller than the number of vertices of G, we can apply induction. Right? So we need to show that C delete V delete Y, number of odd component of this is at most Y for all Y in subset of C delete V, right? So we are applying touch theorem to a smaller component. No, to a smaller graph C delete V, right? So if this is the case, then we knew that C delete V has a perfect matching. So we can assume otherwise, right? So suppose that. So that means there exists Y, which is subset of C delete V, such that the number of odd components is too big, bigger than Y. Right. Now, what does that mean? That means I'm gonna have X, and here's a big odd. What used to be big component, here's Y, and then there are many components, and number of other components here is too big, bigger than y. Now what's gonna be our strategy? We're gonna take x prime to be x union, oh yeah, here's a v, right? X union y union v. All right, now what happens if I delete x prime from graph G? Well, first of all the existing odd components of G delete x still remains as an odd component, so it's -1, right? And the number of other components of C delete V delete Y will be an odd component of G delete X prime. Right? There are other odd components, but we don't care. There's no even components. Yeah. So that's the number, right? That's the number of odd components in the new graph. Okay, now number of odd component in G delete X is X, n is -1, plus what about this? It's bigger than, strictly bigger than y plus 1, right? So this is x plus y. So this is x prime minus 1. So the number of odd component in G delete x prime is at least x prime minus 1. So by 3, x prime is critical. That's contradiction. It's contradiction because we assume that x is a maximal critical set. Okay? Alright. So we have seen that no matter which vertex I choose in each odd component, when I delete it, the remaining has a perfect matching. So what's left is to find those red edges, linking the vertices in X to distinct components. Okay, so how do we write it? Well, that's where we're going to use Hall's theorem or Kinetics theorem. Okay, so let me write the claims. G has a matching M covering X such that each component, I know that every component of G delete X is odd, so each component of G delete X means exactly one edge from M. Right? So I wanna have a, so here you have a matching. I want to have a, have a component. I want to have a matching between X and the components. How do we prove that? Well, you can think of the new graph by contracting these components into single vertices. Right? Contract each component as a one vertex. Now, what's left is kind of bipartite graph. You may still have edges inside X, but no, I'm gonna ignore that. Delete all the edges inside. So then you have some auxiliary bipartite graph, and ignore all other edges, like ignore loops, right? And then this is perfect setting for us to use Hall's theorem, right? Because now it's about matchings in a bipartite graph. So do we have a matching covering X? Yeah, so if G has no such matching, then by Hall's theorem, there will be a subset of X such that so the number of neighboring, so subset of S, the number of neighbors is too small. But how do we say in terms of graph G, the number of odd components? Okay, I mean every component is odd, so let's say number of components of G delete X having a neighbor in S is small. Okay? So let me draw it again. So here's the X. Here's S. Now you have a small number of odd components having neighbors in S. It may have neighbors on the other side. And there are other odd components which may have neighbors in X but not in S. Right? Right. So that's the picture. So what should we do? So let's say X prime be X minus S. This is X prime. And what's gonna happen if I delete X prime instead of X? Now, right? So the components not hitting S, so not having neighbors in S, will stay as a component. So so at least the number of components of G delete X having no neighbors in S. Right? So how many of them? Well, this is X minus number of components of G delete X having neighbors in S, right? Because previously I had exactly X many components outside, and I knew that this number is less than S. So this is less than, it's bigger than X minus S. So this is X prime. So wait, so the number of odd component in G delete X prime is bigger than X prime? So that's contradiction. It's not a contradiction to the maximality. It is a contradiction because we were given a graph G where for any set, when you delete it, number of odd components is at most the size of the set you deleted. All right. So that's it. So that allows you to combine all these things and say that G has a perfect matching. Why? Because take M, that was a matching between these X and components, and the a perfect matching of C delete V of M for each component. C of G delete X, right? Yeah. When you do that, then you have a perfect match. So that's the proof. Of course, there are other proofs as well, and the original proof of thought is a bit different. It's induction on number of edges. So and as long as you keep the inequality, you delete the edge and keep doing it. All right. So now let's talk about some corollary. All right. So remember we had this theorem, this corollary from Horst, that bipartite k-regular graph must have a perfect matching. Can you say something similar? And we're gonna say an analogous thing for regular graph, but in general this is not true. So what happens? I mean, do we need bipartite condition? Here's an example, and let's say it's simple. Yeah, so simple k regular, and do we have a perfect matching? And I'm showing you a counter example. So this graph is simple and 3 regular. Every vertex has degree 3. And it does not have perfect matching, because if I delete the vertex in the middle, I have 3 odd components, and so the number of odd components is too big. And here's a corollary. However, if you forbid something, then you can have a perfect matching. So what do you have to forbid? So let me say a cut edge. So an edge E of G is a cut edge if the number of components of G delete E is bigger than number of components of G. Then we say it's a cut edge. So if you do have something like this, then this is a cut edge. And the next lemma, the corollary, shows that these cut edges are the main reasons why this graph doesn't have a perfect matching. So here's the corollary. If G is 3 regular and has no cut edges, then G has maybe I should yeah, okay, let's do a simpler version. Perfect matching. What I'm debating to myself is whether or not I should say graph is simple, or maybe it's okay without this condition. Let's see what happens. Oh, but it doesn't matter actually, because if graph is irregular, you cannot have a loop. If I have a loop, then that's a vertex of degree 3, and this will become a cut edge. So there's no loop. How about parallel edges? If I have a parallel edges, and if I have a parallel edges, let's see what happens. Okay. So it's enough to count the number of odd components, right? So let X be a subset of vertices. So here's an x. And you have other components. How many edges do we have between x and the other components? The number of edges between x and the other components of g delete x. I'm going to count this quantity in two different ways. So one way is, well, each vertex in x can receive at most 3 edges. So it's 3 times x. And remember, graph has no cut edges, so that means you're not going to have any loops. So every edge is counted exactly once. For the lower bound, each component, right? If I have a component, I will have at least 3 edges. Wait, but okay. Now let me first say a cheating, and then later I will fix it. Okay. So for each component, okay. Oops. Here's a component, and here's a set, and there are no edges between these components. So you must have at least 1 edge. Why? Well, that's the condition. That's the place where I'm going to use 3 regularity. Right. If C is an odd component, of G delete X, then every vertex in C has degree 3. So the number of, if I add up all these degree in this odd component, that's exactly the twice the number of edges inside C plus number of edges joining X and C, right? So edges joining X and C will be counted exactly once per each edge, and edges inside C are counted twice. Why? Because when you look at the vertices, if this is C, then this edge is counted at both ends, and edges joining C and X are counted once. All right. So that means I know that this is equal to size of number of components times 3 because every vertex has degree 3. So this has to be odd. And this is even. So that means number of edges joining X and C has to be odd. Right? So if some number is odd, it cannot be 0. So therefore you must have at least 1 edge. Okay? So the reason why you have at least 1 edge is because the number of edges joining X and C is odd. And since G has no cut edges, number of edges joining X and C cannot be 1. Because if you have a component which has exactly 1 edge joining X and C, then this will be a cut edge. When you delete it, number of components will increase. So therefore, number of edges joining x and c cannot be 1, cannot be 0, cannot be 1 and odd, so it has to be at least 3. Right, so for every component, you must have at least 3 edges towards x. So the lower bound is at least 3 times number of components. So 3 times number of odd components. Right? So from this inequality, we deduce that number of odd components in G delete x is at most x. Right? For all x. Now, let's see where I cheated or not. Is this proof working when x is empty? Did I cheat? No, actually not. In this writing, everything works out. So, in many cases, when you write a proof, you have to be careful whether you're assuming that x is empty or not. In some cases, you may say, well, you can. If I was using the other order, let's say, oh, if I start my proof by saying that, well, you must have at least 3 edges between x and the components because the graph has no cut edges. That's not true. That's not exactly correct because, I mean, without having this step, right? I knew already that x and c is odd, so therefore, no, yeah. Okay, let me say, what's right? If I start by saying that number of edges joining x and c has to be at least 3 because G has no cut edges. If I start my proof, at least 2. If I start my proof by saying this, then that's incorrect because for instance, what happens x is empty, right? C could be everything potentially, and so far we didn't exclude it, so we have to be careful in particular for the case when x is empty. Okay, oops. All right, so that's the corollary, and this corollary is actually due to Peterson in 1891. All right. Yes. So during the homework, you will see many variations of this. Now, the next theorem tells us the size of maximum matching, like a Kinetics theorem, right? So remember, Kinetics theorem says that nu of G is equal to tau of G for a bipartite graph. And in general, this is false. And we cannot say nu is equal to tau in general graph. The easy count example is like odd cycles, right? Nu is 2, tau is 3. And there's arbitrarily big gap, right? You have a graph where nu is way smaller than tau, right? You have many copies of, let's say, triangle. In this graph, nu is number of triangles and tau is twice number of triangles. So the gap is arbitrary. But here's something called Taft-Parrish formula. which was observed in 1958, so many years later, then Touch theorem was proved, which says that nu is equal to something. So for graph G, number of vertices minus twice nu of G. So this is what? This is number of vertices not covered by a maximum matching, right? In other words, if you have let's say graph, if this graph is for people and you want to find the matching, and these are people who are not matched by matching, so those are the people who are single, right? And this is equal to the maximum gap between number of odd components minus size of X. So that's the theorem. So the maximum difference between number of odd components and the size of X determines the maximum number of vertices not covered by, the minimum number of vertices not covered by a matching. So in other words, so we can write a formula in terms of nu, right? So 2 minus number of vertices minus maximum of number of odd components minus X. Okay, so that's the formula. Or if you like the other form, so minimum of among all set, and you have this number, right? So on the left hand side you have a maximum size of matching, on the right hand side minimum of something. So you can think of this as a formula to tell you the size of maximum matching in a graph. But what I really like is this formulation where it tells you something. Why is this interesting? Why is this reasonable? So one direction is easy to see. So which direction is going to be easy to see? So let's see this lower bound. Or, okay, let's try. So suppose, okay, if there is an X, yeah, so if other component, okay, if this number is K, what does that mean? I have an X and I have a K more odd components, and I might still have even components, but I have too many odd components, and all these odd components must contribute at least one vertex not covered by a maximum matching, right? So these X people can be paired with at most one odd components per each, right? And I still have a K left over, and each of these K odd component will contribute one vertex not covered by matching. So if this number is equal to X for some X, then number of vertices minus nu of G, twice nu of G is at least K. So that means, right? So that means this direction is easy. So the left hand side is always greater than or equal to the right hand side. So what's non-trivial is the other direction, right? Why do we have equality? So it's enough to prove the other direction. And that's where we're going to use Tut's theorem. How do we use Tut's theorem? So suppose so let's say K is gonna be the maximum difference between this thing. Alright. So that means for all x, number of component g delete x is m minus x is at most k. So g delete x is at most x plus k. Alright. Now, if that's the case, and our goal, what is our goal? Goal is to find the goal is to prove the number of vertices minus twice nu of g is at most k, right? So in other words, nu of g is at most half number of vertices minus k. That's what we want to prove. So how do we prove that? Here's the idea. Let g prime be g prime is graph obtained from g by adding k new vertices, pairwise adjacent, adjacent to all other vertices. So here's a g. So I'm gonna add the k new vertices, and they are complete. So they are complete to each other, and they are all edges, right? So this is my new graph. Let's say this set is called K, capital K. All right. Now, if I say that this new graph G prime has a perfect matching, then what's going to happen? Well, these k new vertices could be potentially paired with each other, or they could be paired with the vertices in G. But number of vertices that could be paired with the vertices in G K will be at most k vertices, because this set has size k. So the remaining people will be paired with each other. And the size of such a matching is going to be at least size of it's going to be at least number of vertices minus k over 2, because you're going to cover at most k vertices by this perfect matching, and when you delete them, the remaining has a perfect matching. So the size of matching is the number of vertices divided by 2. So that's what we're going to do. So this is what we can show. So it's enough to show that G prime has a perfect matching. Now, why is this the case? Well, let's say let X be a subset of G prime. All right. If X does not cover all vertices in K, then G delete X is connected. G prime delete X is connected. Because if you don't delete all vertices of K, then one vertex will remain, and that is connected to everybody. So it's connected. So that means number path component of G prime delete X is at most 1 because there's only one component. And why is it not an issue? Well, so if X is not empty, then this is okay. So if X is empty, then number path component of G prime is actually equal to, so what is this? I should cover this, right? Yeah. Let me, So here it is, number path component of G prime. But let's look at the K. K is equal to maximum of number path component of G delete X minus X, right? But number path component of G delete X plus X has same parity with the number of vertices of the graph G, right? This is true for every X. So that means K has the same parity. So this is the same parity with the G delete X minus X, because minus 1 is same as plus 1. So K has same parity with the number of vertices in modulo 2, right? And we are adding, so the number of vertices of G prime is number of vertices of G plus K. So this has to be even. So therefore, number path component in G prime is 0. Oh, but am I still cheating? Oh yeah, I mean that's true, because G prime is connected. Let's assume the K is non-zero. Because otherwise graph could be disconnected. But if K is 0, then there's nothing to show, because it's immediately implied by the touch theorem, right? You have a perfect matching. All right, so that's the, so that shows that if X doesn't cover K, then we have a valid inequality. So we may assume X covers K. Then what is number path component of G prime delete X? Well, that's the same as saying number path component of G prime delete K and delete X minus K. But G prime delete K is nothing but G, and we are deleting X minus K. And we are given this property that this is same at most X minus K plus K. But that's same as X size of X, right? So we are satisfying inequalities in Tut's theorem. So therefore, G prime has a perfect matching. All right, so that's the proof. And now you may wonder whether you have an algorithm to find the perfect matching or maximum matching in a graph. And this proof does not give you an efficient algorithm, probably. Yeah, probably not, because remember our proof of touch theorem? There is a step saying that you take a maximal critical set and okay, let me think. Yeah, maybe it may give an efficient algorithm, but right. Because we take a maximal critical set, so whenever we have a critical set, we can grow it by if you follow the proof, you can find the critical set containing it by induction, and then may help. Anyway, later we will talk about the efficient algorithm, polynomial time algorithm given by Edmonds, about the, finding a maximum matching in a graph G. All right, so that's it.